Welcome to Summarize Science, where we break down complex research into ideas you can actually use. Today, we are looking at a fascinating new paper titled Anatomy of a Lie, which explores why vision language models often hallucinate. A hallucination happens when an AI generates a plausible-sounding, but factually incorrect statement about an image. The researchers point out a striking paradox called computational cognitive dissonance. Imagine asking an AI if there is a motorcycle in a photo, and it describes a parked motorcycle in detail, only to conclude that the final answer is no. This means the model failed twice, first by seeing something that isn't there, and second by contradicting its own evidence. This case study shows that looking only at the final answer is not enough to understand if an AI is working correctly. To solve this, the authors propose a new framework that treats the AI's generation process as a dynamic journey. They move away from treating hallucinations as simple output errors and instead view them as pathologies of the model's internal logic. By mapping this journey, they can identify exactly where the reasoning process breaks down. They created 3 specific probes to measure the health of an AI's thought process. The first is perceptual entropy, which measures how confused the model is about what it actually sees in the image. The second is inferential conflict, which detects when the model's final answer doesn't match the evidence it just wrote down. Finally, decisional ambiguity measures how uncertain the model feels at the very last step of its decision. When these 3 measurements are combined, they create what the researchers call a cognitive state vector in a 3D space. Normal, truthful reasoning stays within a dense, stable area of this space, while hallucinations appear as high-energy deviations. The paper calls this the geometric information duality, meaning that a lie physically looks like an anomaly in the data. They even discovered cognitive fingerprints that are unique to different AI architectures. Some models are transparent in their struggles, while others are confident liars whose lies look very similar to their truths. This new detection method, called CD, was tested against several state-of-the-art models and outperformed existing benchmarks. It is much more efficient than older methods because it only requires one single pass through the model's brain to work. This makes it highly scalable for real-world use where we need to check AI answers instantly. One of the most impressive parts of this work is its ability to handle noisy or incorrect data during its setup. The system remains highly accurate even when its training samples are heavily contaminated with errors. This robustness is vital for deploying AI in the real world, where perfect data is hard to find. It proves that we can build diagnostic tools that are smarter than the errors they are trying to catch. To recap, the researchers have moved from just checking if an AI is wrong to understanding how and why it goes wrong. By identifying these unique failure signatures, we can create targeted fixes for different types of AI errors. In the future, this could lead to AI systems that are fully auditable, meaning we can see the logic behind every word they say. Ultimately, this brings us one step closer to building trustworthy artificial intelligence that we can rely on in high-stakes situations. The diagnostic nature of this framework opens up exciting possibilities for self-correcting AI. Imagine a model that notices its own perceptual entropy is too high and automatically zooms in on the image to double-check. This study is a major milestone in making the black box of AI a bit more transparent for everyone. Thank you for watching Summarize Science, and stay curious about the world of technology.